Hello 171 class. This is part 3 of your notes on 2.5. This is just another example of finding the zeros of a polynomial using the calculator, synthetic division, using the remainder theorem. The first zero, according to our table, I've got this in my calculator. The first zero I see according to the table is 2. Okay. So if I do synthetic division on this, alright, so there's the setup. 1, there's a 0 for the cube, -6 for the square, -8, 24. Okay, and remember we just start here, multiply, add, multiply, add, multiply, add, and then multiply. Alright, so we get this. Now, remember, this is x cubed, x squared, x, the constant, and then this is the remainder. What I said in your notes earlier is that we have to get down to degree 2 so we can use the quadratic formula. Alright, again, I got the function in the calculator. If I graph it, again, I can see this is my window is -5 to 5, -50 to 50. So when I graph it, remember, this is positive leading coefficient, even degree, so it rises left and right. It's degree 4, so it's got 3 possible bends. There's 1, 2, 3. So there's my 3 bends. So this is the complete graph. This is the only 0. Okay, if you trace it, we can see there's the 0. If I zoom there, as many times as I want to zoom, I can get closer and closer and see that it just turns and touches. It doesn't cross and cross again. So because it turns and touches, this is even multiplicity. So that means that I'm going to be able to do synthetic division on this degree 3 polynomial. Okay, and the way we do a repeated iteration of synthetic division is we just put, because this was a multiplicity 2, or an even multiplicity at least, that means I can put that number again and do synthetic again on this polynomial, stopping at the -12 now. And I see, because that's a 0, that meant that that was in fact multiplicity 2. I mean, we could see it from the graph because it turned and touched. But that just means when it turns and touches like that, that 0 will work again on another iteration of synthetic division. Now, that means that we're down to, this was x to the 4th, this was x cubed, now this is x squared, x and the constant. Or as far as the quadratic formula goes, this is a, this is b, and this is c when we plug into this quadratic formula. So I get -4 plus or minus 4 squared minus 4 times 1 times 6 over 2 times 1, and then all this stuff in the underneath the radical here, 16 minus 24 under the radical. Right, and because -8 has a factor of -4, I can write this as -4 times 2 over 2, and then -4 reduces, the square root of -4 reduces to I times the square root of 2, and then just like we've done several times with the quadratic formula, when this number's 2 and these numbers up here are both even, we can reduce both of those by 2. So -4 divided by 2 is -2, plus and minus 2i square root of 2 divided by 2. Those 2's will cancel, and we're left with I square root of 2. Alright, so overall we have 2 of multiplicity 2, and then we have both of these. Alright, so there's an example with imaginary zeros. Okay, remember, degree tells you how many possible x-intercepts you have, the most you could have. You don't have to have that many. Then you have to start remembering graphically about multiplicities. So that's how I knew to do 2 a second time, is because of that touch and turn there. It means it's multiplicity 2. That means that 0 counts more than once towards the 4 that we're talking about here. And then because the end behaviors, it rises left and rises right, it's not going to touch anymore. So it touched here, that counts as 2. The other 2 times, it's not touching. That's why we're picking up the imaginary zeros. The final 2 solutions to this equation are not real numbers. And I can tell that graphically once you start getting used to what we mean by real zeros and imaginary zeros. Real zeros, you can see them on the x-axis. Imaginary zeros we can't see on the graph.